session 2 of this FTP on MATLAB for mechanical engineers. In this session, I will be handling the ordinary differential equations topic. Okay, so in this topic, we will try to understand how we can write down differential equations for some of the physical systems in mechanical engineering, and try to solve those differential equations by different methods that is already known to us. Okay, all right, so let me bring you the outline for this session. Okay, so we will try to have a small introduction on ordinary differential equations, try to understand what type of differential equations we'll try to solve in this session. Then the solution technique for solving the ordinary differential equations will be discussed, where I will try to give you a standard solvers in MATLAB and discuss how an iterative technique of solving ordinary differential equations can be accomplished using scripts and functions. And then we will try to move on to the case studies, where we will take some examples of writing a differential equation for a simple mechanical element, which is the dashpot, to yield a particular order differential equation. Then we will try to solve some of the problems on Newton's law of motion. We will then extend the techniques that we will learn in these case studies on solving these two differential equations for a dashpot and for Newton's law of motion to problems on vibration. In vibration, we will try to cover up two classes of problems. The first one is a free vibration problem. The second one is the forced vibration problem. So from this case studies, we will try to understand the overall sense of how ordinary differential equations can be solved. This session is focused towards solving only ordinary differential equations, and the scope of this session is not to cover up differential equations that govern the physics of the problem through partial differential calculus. So I will not be covering the partial differential equations. So we will only stick to ordinary differential equations in this session, and we will try to understand some important conclusions from after which we have programmed or written a script for this class of problems. Okay, so if you have any queries or clarifications, please do type it up in the chat. Okay, I'll be happy to answer it. Okay, on the go when I start explaining the slides. All right, so let's get into the introduction. Now, in ordinary differential, any differential equation can be classified based on the order of the derivative. Suppose you have a differential equation. The highest order of the derivative in that differential equation classifies that differential equation into an order n. Suppose you consider a differential equation of the form dy by dt as function of time and y, okay, where y is a dependent variable and t is the independent variable. Now, if you take dy by dt is equal to function of t comma y, I might have any function of t comma y. It can be an algebraic function, it can be a polynomials in t and y, and it can be a function, trigonometric functions, hyperbolic function, so on and so forth. In general, a transcendental function. So if I take this differential equation of this form, where you will have the first derivative itself given as a function of time and the dependent variable y, then this equation has order 1 because you will only have one derivative. So you will call this as a first order ordinary differential equation because you only have derivative with respect to time and nothing else. So this type of differential equation um, is well known for most of physical systems which are bound by the first order variation of the dependent parameter, which is y in this case. Now, if you take a differential equation with a higher derivative, okay, suppose you have the second derivative of y with respect to time, okay, so you will have this term, which is the first derivative, being differentiated again with respect to time, then you will have d square y by dt square. And this second derivative is now function of not only t comma y, but also a function of the first derivative. So you will have d square y by dt square equals function of t comma y comma dy by dt. Now, if you have this type of a differential equation, you can clearly see that the order of the differential equation is 2. Okay. So if you have the highest order of the derivative in any differential equation, then the order of the derivative Bn, then such kind of differential equations, which are ordinary differential equations, are termed as nth order ordinary differential equation. In this case, you have a second derivative, so you will call it as a second order ordinary differential equation because you only have y, which is a dependent variable that only depends on time t or the variable t. Okay, so y is only function of t, so it is an ordinary differential equation, and the degree of the differential, the order of the differential equation is 2, so it is a second order differential equation. Now, suppose you have d square y by dt square to the power of 2 is equal to function of t comma y comma dy by dt. Okay, so if you have this kind of differential equation, then this second derivative to the power of 2, suppose you take the second derivative to the power of 2, then 2 is referred to as a degree of the differential equation. So you will have 2 here as an order of the differential equation because you have the highest derivative here, and to that highest derivative, if you have a power, okay, then you will have the power to be referred to as the degree of the differential equation. Okay, so in this session, we will try to restrict ourselves to solving only the first order ordinary differential equation and the second order ordinary differential equation, because most of mechanical engineering problems deal with using solving to yield a solution using some of the differential equation methods or solution techniques. Okay, they fall in a class of solving the first order differential equations or the second order differential equations. Okay, so now let me just try to give you an overview of what type of solution techniques are covered up in solving the ordinary differential equations. Okay, so if you look at most of the differential equations, there are quite a number of methods that is used by the engineers to solve different class of problems, especially in the field of rigid body mechanics, in the field of elasticity, so and also in other fields, namely the thermal fields and fluid flow fields, and many other associated fields that is being taught by mechanical engineers. So we will not try to cover up all the solution techniques, but we will try to take up some of the simple solution techniques, okay, that is restricted to the mechanical domain. Okay, so the solution to ODEs that I'll be trying to discuss generally fall in the category of exact solutions or a numerical solution. Okay, so that is where I will try to explain the solutions for a class of ODEs that I'll be solving in this session. All right, so as I've discussed, you will have a solution to ODE, okay, through exact or analytical methods. These are some of the mathematical methods which can give us an exact solution. And it is also known as an analytical method because you don't need to use a calculator or a MATLAB to obtain a solution. If you just have the prerequisite of how to use the calculus, you will derive the solution by using numerical derivatives and integrating the derivatives. So it is a pen and paper calculation methods. So you have to use only the integration charts or your derivative charts to refer to how a differentiation or integration can be done in the exact sense. Okay, so these methods are simpler as compared to any other methods, and in MATLAB we will try to use a specific command known as dsolve. Okay, so to obtain an exact or analytical solution, okay, to a given ordinary differential equation, restrict ourselves to the first order and second order differential equations, we will try to use this command known as dsolve, right? So then we will move on to the computational methods or a numerical solution. So these methods that we have use a successive estimation of the derivatives, okay, by using a certain time step or the space step. Okay, so you will try to use a time step or a space step, okay, to solve these ODEs using numerical methods. Now, example of these numerical methods are Euler method and Runge-Kutta methods. Okay, so this has been taught in the undergraduate course, so I will not be covering up the Euler method, but I will try to focus to understand how a Runge-Kutta method works, which is an iterative method and a numerical technique. And we have a popular method, which is RK4 technique, Runge-Kutta fourth order estimation of derivative method. Okay, so we will try to make a program or write a script to accomplish how an RK method can be used to solve a particular ordinary differential equation. The third class of solution that you would be interested to look in for ODEs are the semi-analytical methods. So here what you try to do is you will do a formulation, or you will try to solve the differential equation to get an equation to reduce the derivatives. Okay, and then once you reduce the derivatives, you can use linear solvers or an iterative techniques to obtain the solution. So this type of methods will not be covered in the presentation that I'll be presenting from now onwards. Okay, so it is beyond the scope of the study for this session. Okay, so I will try to cover up these analytical methods and iterative method. A general solution to any analytical or iterative method that we obtain using MATLAB is to use our dsolve command. Okay, so we will try to use a dsolve command. In addition to that, this command can only be used for your exact or analytical methods. So differential equation which has a exact solution, you will try to use this dsolve command. But if you take if you want to do a numerical solution to this ordinary differential equations, then you will have to use an differential equation solver known as ODE. Okay, So it's there is a command known as ODE, and there are class of differential equation solver by the name. Okay, so if I say ODE 45, it will use Runge-Kutta fourth order and fifth order method in conjunction to solve your ordinary differential equation by iterative method. Okay, so we will try to also discuss some of the problems using ODE 45. Okay, so this is about the solution of the problem. So what I want you to do is uh, as and when I try to make up a program, please I will try to paste the program in the chat, and you can also execute that in your computers, and we will have some discussion session. Okay, to exchange what outputs you are getting while I try to code the program. Okay, or write a script. Okay, so the first command is to solve an ordinary differential equation which has this form: dy by dt plus 3y equals 100. So now if I want to solve this problem, what you could do is you could integrate this. Okay, you will do an integration once, okay, to this differential equation to yield a general solution. Now if you want to actually get a general solution, after you integrate this differential equation, you will end up getting a constants, okay, which are also known as constants of integration. So those constants that you have, okay, have to be evaluated based on the conditions that is specified for this differential equation. Please note that if you have the first order differential equation, then you will have only one initial condition, or a condition which says y at a particular time, okay, is defined by a certain value, a real value. Okay, so if you have a differential equation and the condition that's given to you, then you can get a particular solution. Okay, so we are only interested to obtain a particular solution for most of class of engineering problems, but what we try to also do is first obtain a general solution and then march on to get your particular solution for the imposed conditions. Okay, so the MATLAB command, which is dsolve, solves this differential equation with the following syntax. Okay, so you will have to write the equation, you'll have to write the differential equation, okay, and you will have to specify the conditions, okay, which will give a value to the constants of integration, and you will have to also specify that what is the independent variable through which you want to actually obtain a exact solution. Okay, so a typical command for you to solve this problem would be in this sense. So if I take dsolve, if I type dsolve in the command prompt, and if I have capital D here, capital D refers to the derivative operator. Okay, so if you say capital D, you'll have d by dt. All right, so d by dt plus 3 times y is equal to 100. So that is your equation that you write within the quotes. So please never forget to write the quotes. This differential equations that you actually enter will be in the form of strings. Okay, then you'll have to specify the initial condition for the dependent variable y, so which is y of 1 is equal to 0, for instance, that I have taken that at time t equals 1 second, y of 1 equals 0. So that will be now solved with respect to an independent variable t. Okay, so if you try to execute this command, dy by dt plus 3y is equal to 100. Ajay has a doubt, can we write dy by dt as dy by dt? No, it will not accept that because capital D is a differential operator. Okay, now let me get into the MATLAB. Dy by dt plus 3y is equal to 100. Okay, so I will say dsolve dy plus t star y is equal to 100. That should give you, and y of 1 equals 1. Y of 1 equals 0. Sorry, 0 comma t. So this gave us a solution in the form of answer. So if I type answer, so that is a solution that I get. So this solution is now a particular solution. Now what I want to do is okay, I will try to copy this. Then,
Santosh sir, excuse
yes,
me.
yes sir.
Can you please increase the font size for that MATLAB this one window?
Santosh, you can
So
use
that's what I
the
was
zoom
asking you,
option
sir.
in Mac actually. Yeah, screen zoom option is there, no? Screen
Now
zoom,
is
that's
it
what I
coming?
told.
Is it visible?
No,
Yeah, now
no, it is visible, but it
little
is
bit
very
screen
small.
zoom use. No.
So
Small.
should I have to
Screen
go
zoom
for
use.
some view?
Screen zoom.
And collapse.
No, not that. Wait.
No, use option plus command option plus. I think in Mac, no, we have option command
Santosh sir,
option plus.
on your keyboard you just press that command and plus.
Plus. Command, that is command.
No, it won't increase the.
No, it will increase. Zoom size, it will increase. Command option plus or equal. Yeah, plus you can use. Command option. No, not this one. You on using
Right.
the keyboard, you type command option plus.
Command option plus.
Yeah. That's to zoom.
Command option and plus. Okay. No, sir, it's not working.
Because your fonts are very, very small.
Sir, you can
Sir,
use
you go
control
to-
and plus.
Control
And plus.
Control and plus. I did that
Yeah,
first.
both should be. See, control, option, and plus. All three should be at one go.
No.
Okay.
Okay.
Control option and plus. No, it doesn't work.
Otherwise, if you are using the mouse, actually, you can use control and zoom in. That is, you can
control
just
and
scroll up.
move
Scroll
mouse
up,
inwards.
scroll up you can do. Yeah, scroll up you can do. If you're using a mouse.
Control. What is it, sir? Control.
No, if you're using a mouse, no, you can use control and scroll up.
Control and.
It will work. In Mac, it works actually.
No, it's okay. Santosh sir, what you can do is in your MATLAB window only go to home, click on the home,
Yeah.
What you do,
home,
otherwise,
click on preferences. Preferences. Besides that, layout preferences is there.
control. If you
Right.
Swipe upwards.
Okay.
Yeah. Here preferences. You can see that gear symbol.
Yes. All right.
Click there. Click there. Go to this one. Fonts. Command window
Font?
below fonts. Go there.
Yes.
Increase
There
fonts
you
to
change
maybe
the
20.
font size. Make it
20.
15 or something.
Okay.
14, 15. See, you can maybe
Make it
type
18,
15.
14
Yeah.
or 18.
Yeah.
Yes.
So apply. Say apply. Click on apply.
Yes. So it is zooming a bit, right? So
Yeah, now it's coming. Now it's zooming.
okay,
You
bigger.
can make it 18 probably.
Now is it visible?
Yeah.
It's fine. Yeah, it's fine.
Okay, so
Yeah, this
meanwhile,
might
I'll
take,
also copy and paste the command in the chat if you can't see it. Okay, that also I'll try to do during my presentation. So okay, fine. So all of you did this, executed this command. Hope so. You would have done that by now. Now, if you try to solve the same differential equation, okay, without even specifying the initial conditions, then you will have a solution given by dsolve command. Now, since it is only the first order differential equation, you will have only one constant given by C2. Okay, so if you specify this initial condition, you can solve this, solve for C2, right? And then once you solve for C2, you substitute back for C2 to get your particular solution that we did in the previous case. All right, so once we have an exact solution that is defined for a problem, what we'll try to do now is to understand that if you have an nth order derivative, suppose you have an nth order derivative, okay, then suppose you have an example like d power n y by dt power n is equal to 3y is equal to 100. So with this, my derivative is of order n, where n is generally an integer, then you could also solve the same problem with dny, where n stands for any integer. Okay, so that's how you also solve an higher order derivative differential equation with such higher order derivatives. All right, now let us move on to some of the case studies. Okay, so once you know how to solve this in the exact sense, we will try to go for some of the simple application problems. Now let us take a specific problem. Let us take a dashpot. Okay, let us consider a dashpot. Now if you take a dashpot, you will have a cylinder within which you will have a movable piston, right? So if you apply force to this piston on this end, you will see the displacement of the piston within the dashpot. So if I take that force f of t as a force that I apply in the end of the dashpot, then I can push this piston, okay, through a viscous fluid. Now it can be an air or a fluid, okay, with a certain viscosity. Then you will see that there is a resisting force that is applied on the other face of the piston here from the fluid, whose magnitude is proportional to the velocity of the dashpot here. So if I take x as a displacement of the piston, then the derivative of x with respect to time is the velocity. So this velocity will be directly proportional to the applied force. So if I introduce that constant between the force that is applied and the velocity, that constant c is the dashpot constant, or it is also known as a damping constant, because it is a dissipative phenomena which tends to decrement the energy or of the work done, which is F into X. That's the work done. So it will decrement that energy in the form of viscous flow friction. Okay. Therefore, if I take that f of t, like we discussed that in the last session, that there is this force, that is error force, that is applied for a first order control system. Now anyway, now let us take that as an example here. And if you have the function of a force as a function of time, that is given as an exponentially decaying force, which is e power minus t by c, then you will establish a first order differential equation for the motion of the piston, or you will try to find the derivative of the displacement of the piston. Okay, so that is to be now found out. Now this is a differential equation, and you will simply solve for your x of t. Now what you'll try to do is, for a simplified analysis, let us consider C to be 1 and C is equal to 1. Then you will solve this differential equation in the following sense using the dsolve command. So I can take dsolve of this with the initial condition that x is equal to 0 at time t equals 0 and execute that in the command prompt. So we'll have that executed here in the command prompt. So if I see the solution to this problem, which is having an exponentially decaying force with C to be 1, okay, so if you solve this with the initial condition x of 0 equals 0, then you will see that the particular solution, okay, is 1 minus e power minus t. Okay, that's the particular solution that you have. So I will copy paste this and put it up in the chat. Okay, so there is a command that you can try to use to execute this in the command prompt, this command in the command prompt to get the solution. So your solution is now 1 minus exp of minus t. Now what we'll try to do next is that we computed this using Laplace inverse in the last session. Okay, we got the exact solution by Laplace transform, if you just recollect. Now you are trying to get it with respect to a standard command known as a dsolve command. Okay, so what is the next thing that we'll try to do is try to give you or try to plot the solution in time. Okay, we'll try to plot the solution in time. So if you take your constant c, okay, I can take it as a constant c here as your dashboard constant, and if I take c to be 1 as what we have done here, okay, yeah, we did it for c to be 1, right? Okay, so when we do that and create a vector of t starting from 0 to 10 seconds and plot that value of x of t, okay, which is an exact solution, I will get the following plot. So if I run this code, I will get the following plot. So you will see that this is as and when the time varies, okay, your displacement of the plunger or the piston also varies and will settle down to 1. Okay, so this is the variation of your x of t. Okay, now if you can recall your control engineering problem, you actually gave a unit step function to the control system. So the input was 1 for all period of time, so that was our r of t. So if I try to continue running this problem, I will have the following plot. Okay, I'll have the following plot here, where you will see a line here, which is a straight line, right? So that is the input, which is r of t, and this is the output x of t. So you will have response here and the time here. So you will have r of t to vary with respect to time and settle down to your input. The x of t to vary with respect to time and settle down with respect to r of t. It will have the same value. Okay, so this is one good example of understanding how a response with respect to time can be plotted using an exact solution. So we got an exact solution to the ODE using dsolve, and you could plot that. All right. So now what we'll try to do is solve the same problem using an iterative method, which is your Runge-Kutta method. Now, Runge-Kutta method is actually a differential equation solver. It is an ODE solver. Okay, it's an ordinary differential equation solver, and it uses successive estimation of slopes. So you will have slopes to be successively estimated. That means the slope at the current step is estimated based on the computed slope in the previous step. Okay, so if you just take this first order differential equation, suppose you take this first order differential equation of this form, dx by dt equals f of t comma x, okay, with a prescribed initial condition x of t 0 is equal to x naught. So this is your initial condition as what we had specified in the previous problem. Then your solution depends on the time. Okay, now what we'll try to do is we will set the time to have an initial value which is t naught. Okay, and the next value of time tn plus 1 refers to t naught plus an incremental step size that is known as h, or you can also call it as delta t. So tn plus 1 equals tn plus delta t. Okay, so once you have this variation of this time with respect to a constant step size, you can estimate the corresponding slopes xn plus 1 using the previous value of xn that is computed using the following RK4 formulae that is given here as h by 6 k1 times 2 times k1 plus k2 k2 plus k3 times k4. Okay, so this is the approximation of the next value of x based on the previously computed value of x using the weighted slopes k1, k2, k3, k4 are your weighted slopes. Now if you can remember, slope is now a function of t comma x. So if I write k1 as a function of t comma x, where I take a particular value of time, okay, at a known interval and the corresponding value of x that is already computed in the previous computation, then I can find out 4 slopes k1, k2, k3, k4, okay, based on the time step. Now k1 is evaluated at the starting time step, k4 is evaluated at the end of the interval tn plus 1, whereas k2 and k3 is evaluated at half the interval, which is h by 2, okay, or the half the time step. Then you will have k2 estimated based on k1 and k3 estimated based on k2, and k4 again estimated based on k3. Okay, so once you have this weighted slopes here, the weighted slopes, okay, if you multiply this weighted slopes with h by 6, okay, you will add that to xn, you will get your xn plus 1. So that's how you will successively approximate the values of x for a time step that you take in this form, tn plus 1 equals tn plus h. Okay, all right. So what we'll try to do is we'll solve this problem using solve the first order differential equation of a dashpot using your RK4 method. For that what I'll try to do is I'll give you the code. Okay, that's the code that I've given up. I've just pasted that in the chat box. You can refer to that. So code here for RK4 technique goes as follows. Okay, so first I'll start with the initial condition. Now my initial condition, as we have taken for the exact solution, is the displacement of the piston at time t equals 0. Then I will try to move forward with a time step of 1 second because we are simulating the solution from 0 to 10 seconds. Okay, we're computing the solution from 0 to 10 seconds in the span of a uniform time step of 1 second, which is delta t. So the number of steps that I have to move through is t final minus t initial by delta t. So that gives me the number of steps. So once I get that number of steps, what I try to do is make up a vector of time 1, where we have a time stepping from 0 to 10. That's what we have done here for time t. I'm using a different variable t1 because I don't want to clash this values of this these values of this variable time 1 with respect to t. That means I don't want to clash with the vector of um, t with respect to t1. So what I've done is I've created a new variable time 1. Now once I do that, what I'll try to do is I will have, if there are n time steps, I will have n plus 1 endpoints, where I will have for each of these endpoints the value of x to be computed. So I will make a vector of 1 row and n plus 1 column. Okay. Now what I'll try to do is first what I'll try to do is I will populate that x, which is for all the rows and first column. What I've done is all the rows is there's only one row here because it's RK4 for first order system, and 1 I will start with the initial guess x naught. Okay, so once I have all the values of delta t, which is h in the presentation that I gave, and I will have the corresponding values of initial time and the final time that I want to step through, that I want to run the differential equation. Then I will start running a loop to estimate the values of k's for each iteration. Okay, so I will run the iteration. Okay, so I will compute the value of k's using the function, okay, called as OO derivative. So suppose I open that function as OO derivative.m. What I've done here is that since your derivative, which is dx by dt, is equal to the force value in time is now given as an expression. So that expression is exp of minus t by 1, where the dashpot constant was 1. So I will make a function dx equals this, with passing an argument of t and x. Okay, and the first I will create a vector whose first element is equal to the value of the derivative that is given by the expression exp of minus t by 1. So once I do that, I will call that function here. That means you're trying to estimate the derivative again and again by passing on what is the value of time. The time is now time 1 of I, okay, comma xi. Xi was the previous value of x that is given by the initial condition. Now k2 is again estimated with a small modification where you will have to introduce delta t by 2, which is h by 2, and xi plus h by 2 times k1, that is computed in the previous command, and so on and so forth. We'll compute k3 and k4. So once you have k1, k2, k3, k4 lined up, you will have the new value of x that is estimated is the old value plus h by 6, which is delta t by 6 times k1 plus 2 times k2 plus k3 plus k4. Okay, so once I get this value of x new, that is when I have stepped through in time for one delta t step. Okay, and that value I will try to store in another variable, which is capital X. So in this way, for one iteration, as what we have discussed as a loop constraint, you will estimate the value of x. So for the next iteration, you will again have a different time step, which is given by time 1 of I. So time 1 will step through 2 times delta t, and the following loop will run. So if I perform this computation, if I run this computation, okay, I will have a vector x whose columns will represent the values of x that got computed using RK4 method for a corresponding value of time step that we have created as a vector called time 1. Okay, and then I will try to plot this solution. So if I run this code and continue this code, I will have the following plot. So as you can see that when I did this plot command, I did red square here. Okay, red square refers to the data points that got computed using RK4 method. So what I try to do now is I will try to zoom it up a little bit and see what is the red square, where is it lying about. You can see that the blue line, which is a data point here, which is represented with a blue circle and a continuous curve, you will see that is exact solution, and this is your RK4 solution. So you will see that there is still an error. The error for this method is of the order of h power 5, or order of delta t to the power of 5. Okay, so that is because the method is sensitive to the step size that you take, which is delta t. Smaller the step size that I'll try to take, then the error vanishes. Although the error is less, it is in the third decimal place, as you can see in the screen. We should be happy that we have at least got into a trend in a graph depicted by the exact solution. So we have the match of the exact solution points at equal time steps and the corresponding points that got computed from RK4 technique. So what I'll try to do is I will try to copy this code and paste it up in the chat here. Okay, so that's the code that I've typed it up there. Okay, and then what we'll try to do is I will also give you the function that I've called in the main script. Okay, and I've typed that and I've pasted that in the chat window. So if you try to execute this main script with the function file, okay, you will end up evaluating the data points from the exact solution and your RK4 method to successively estimate the slopes. So what we have done until now is, for this class of differential equation that we have, c into dx by dt equals e power minus t by c, we have solved it using exact solution when we could plot that, and we've used a numerical technique, which is an iterative technique, a popular iterative technique, which is RK4 method, and we could get the solution in the numerical sense. Okay, so if you have any clarifications, then I can take up some questions, otherwise I can move on. Is it all right? Yes, Abhiram, you have to define first before you get into the loop. So you will define that function because you have to first get the value, get the expression for the derivatives. Okay, so once you do it, then you can easily start calling them within the main script. All right, okay, fine, good. So let me move on to the next class of problems, work case study 2. Now, case study 2 deals with the second order differential equation. So we have this popular Newton's second law, okay, where we have the change of momentum of a particle in time is equal to the applied force. So that's a statement that Newton's law actually gives you. So if you have an imposed force on the particle, you will try to accelerate that particle. Now, if you have this, if you expand this momentum into m into dv by dt plus v into dm by dt, what will happen is that this term has to be neglected. Why? Because that the velocity of the particle is very less as compared to the speed of light, and the mass that you have is conserved. So you will take out this effect from your Newton's law, and you will use this for motion of all particles given by F equals m into dv by dt. Now v is now a velocity, so you will have the second derivative displacement given as an acceleration. So m into d square x by dt square is of F. So if you just take this equation, it is a second order differential equation. Okay. Now if you look at the initial conditions, you will have to have two initial conditions. One is for your displacement x, and the second one is for your velocity dx by dt. Okay. So only if you have two initial conditions, you can arrive at a particular solution in time. So the best way to solve this is using an exact solution by double integration, or you can also perform Laplace transform. Okay, both of this method will yield you an exact solution. But if you want to get a numerical solution, you can go for, as I mentioned before, an ODE class of solvers in MATLAB. Okay. ODE 45 is an higher order solver that uses Runge-Kutta method. So if you can see, ODE 45 also solves this differential equation, but it is a class of solver which has this numbers associated with that, 4 and 5. 4 stands for RK4 method and 5 stands for RK5 method. RK5 method is a Runge-Kutta fifth order method. So you will have 5 slopes that will be estimated, like K1, K2, K3, K4 and K5. And with using RK4 and RK5, they will try to have an adaptive time stepping algorithm. So this method have to be coded, but this is out of the scope of the syllabus because we already have a standard MATLAB solver, ODE 45. The use of such solvers requires us to have a prior knowledge of how to actually take a higher order differential equation and write down an n first order differential equation from that higher order differential equation. So that is what we'll try to understand now. Now, if there is nth order differential equation, then you'll have to write a n first order differential equation. Okay. So if there is a differential equation of the order 2 here, as you have seen, you have to write n first order differential equation. That means now n becomes 2, so you'll have to write 2 first order differential equations. So once you write 2 first order differential equation, that is the input to this class of solvers, which is ODE class of solvers. So how do we do that? Now let us take 2 variables. Now since it is a second order differential equation, I will take 2 variables, which is x1 and x2. Okay. X1 represents physical displacement of the particle, where x2 represents the velocity of the particle. So if I take x2, which is a velocity, that becomes a derivative of x, right? So if that is a derivative of x, then it becomes dx1 by dt. dx1 by dt, I will write it as x1 dot. Okay. So x2 is now related to x1 by this equation. x2 is equal to x1 dot. What we are trying to simply say is that the velocity x2 given by second variable is a differentiation of x with respect to t, which is now a differentiation of the displacement with respect to time. Okay. So x2 is equal to x1 dot. Now what we try to do, if you go to the Newton's law, with x2 is equal to x1 dot, now x2, which is velocity, is x1 dot. So what will happen if I substitute x2 is equal to x1 dot here? I will have m into x2 dot. Okay, x2 dot, because x2 is velocity, x2 is equal to x1 dot, but now we'll have derivative of velocity, so we'll have m into x2 dot. Therefore this equation now becomes f is equal to m into x2 dot. If that becomes m into x2 dot, then if you suppose that you have a unit force applied on a unit mass of 1 kg, then you will say dx2 by dt is equal to 1. So that is the second equation that I have. x2 dot is equal to 1 here. Okay. I will always set the initial conditions to 0. So your initial conditions for displacement at time t equals 0 is 0, and the particle has a velocity of 0 at time t equals 0. So you will have two differential equation now. X2 is equal to x1 dot, or I will say x1 dot is equal to x2, x2 dot is equal to 1. So there are two differential equations. So this is what I was trying to tell you. These are state space equations. Now what you have to do is take a second order differential equation, split it up into two first order differential equations. That's what we have done here. The first differential equation is this, x1 dot is equal to x2. Second differential equation is this, x2 dot is equal to 1. So once you do this, then you can use this class of solvers, which is ODE class of solvers. All right. So if you see the standard syntax of this ODE solver, okay, you will see that you will have the solver to give an output of two vectors. So those vectors are t and x, but t is a vector of time and x is a vector of your velocity and displacement, because you gave in two derivative equations, which are two first order differential equations, to this ODE 45 solver using a function. So you have to write a function for these two differential equations, first order differential equations. Okay. And in addition to that, you should also specify the time interval for which you want to run the solver to successively estimate the slopes of these two differential equations. And then you have to specify the initial conditions. Okay. So this is the standard syntax of your ODE solver. If you know how to break up an higher order, nth order differential equation into n first order differential equation, code all of those derivatives in the function name, and then supply the initial and final value of time and give an input as an initial conditions. Through this ODE 45 solver, you will solve this equation to give two vectors. One, the time vector, for which it will take an adaptive time step, and x is a vector of those displacements and velocities. Okay. All right. So once you have that, you will get t and x as column vectors. Okay. Now we will use this ODE solver to solve some problems especially to solve this Newton's equation of motion. Okay, so that code I'll try to open up. Okay, so you have a Newton's law. Okay, so you will try to solve the Newton's law of motion for a particle. In this code, you will try to estimate that with a double integration, setting the initial conditions as 0. That means the displacement at time t equals 0 and velocity equals 0 at time t equals 0. And if you perform a double integration, you will get x equals t square by 2. And that is the solution, exact solution to the motion of the particle in one dimension. So once you do that, you can also use Laplace command, okay, to execute and get what is your displacement. Okay, so that also turns out to be t square by 2. So you can also do an f plot for that. So if I execute this script by doing a clear all in the command window, you will have as a plot. You will have a plot here. Okay, you should clear that. Okay, here. So if I put a pointer here, yes, there it is, and execute this program. Yes, there it is. So you will have the series of points that got computed using the double integration that you did. Okay, you can also use a desolve command that is available in MATLAB to do that. Then next, what we try to do is we'll use a Laplace transforms to execute this before we get into ODE. Okay, there we go. Here, so those dotted lines will represent a solution from that's an fplot, a solution using fplot command to plot the solution using Laplace transform. I've used the inverse Laplace transform here with the symbolic variables. Okay, and third, we will try to execute the iterative solver, which is a ODE45 solver. For that, I have to now write down the derivatives. Okay, so if you can recall that you had x1 dot is equal to x2, that's the first differential equation, and x2 dot equals 1. Okay, so these two are the derivatives that you have to code it up in the function file. So what I have done is I've defined dx as a vector of 2 rows and 1 column. So if I take the first derivative, dx1 dot or x1 dot, that will be equal to x2. That's what I've done here. And then I take this second equation, differential equation, x2 dot is equal to f by m. Now I'll set force to be unity, and that's acting on a mass of 1 kg. So dx2 is equal to 1. So if I have this dx1 and dx2, now that is the two derivatives that I have to code within the function file. So once I do that, I can call them using a standard ODE45 command. So if I say B Newton state space, which has an argument of t and x, I will call that here, and I will have the time to vary from 0 to 1 seconds, and my initial conditions are 0. So if I do this and try to solve this, okay, try to solve this by continuing in the program, you will see that it generates two vectors, time and disp. Okay, so this vector time, if I just try to type the time in the command prompt, you will see that the time varied from 0.001 second, and it dominated at 1 second. And you look at the time step, it did an adaptive time step. In RK4 method, we took an uniform time interval. You see, delta t was a constant value, but here you will see the time steps actually varied. So it is an inbuilt solver in the MATLAB that decides the time stepping of how to estimate slopes. If there's a larger variation in slopes, then it will try to take more time steps, and if there is a smaller variation in slopes between two successive computation, it will take larger time steps. So this type of adaptive time stepping algorithm is embedded in this command ODE45 in MATLAB. And then what we'll try to do is we'll try to continue and plot that. Okay, and time versus DISP of all the rows, first column. And I said this, it will give me a vector which is a 2-column vector, okay, of displacement here and velocity. Okay, so you will, if you want to, the solver will solve for both the differential equation, provide a solution to both the differential equation by estimating the displacement as well as velocity. So the first column is now the velocity, sorry, the displacement, and the second column is the velocity. So you will have displacement vector given by this column and the velocity vector given by this column, okay, for all values of time. So you can see that if you see the size of this time, it is a 57 cross 1 column vector, whereas displacement is 57 cross 2. So for every value of time, you will have 2 columns with first column representing the displacement value, the second column representing the velocity value. So then I continue this code to plot your time versus displacement using ODE class of solvers. Okay, if I do that, There you go. You see here. So we did an exact solution based on Laplace transform. So you had an exact solution, Laplace transform solution, ODE 45, and I've also done RK4 that I'll be trying to explain. Okay. So this ODE 45 yielded you all of these star points here, all of these star points. Okay. And the red square is a RK4 method. RK4 method now is a higher order method because this is solving a second order differential equation. I'll get back to this, but before that I will paste this code to you. So what you try to do is you please try to execute that in your computer. Okay, that's the code that I've pasted here. And what I'll try to do is also give you the function file that I've used here. There you go. That's the function file. So this will cover up an exact integration scheme. Then you'll have a Laplace transform, and then you will have an ODE45 solver. Now, what you have to do here is if you want to use your RK4 method, okay, it is absolutely the same program that I've written, nothing else, no difference. But what is a change that you will have to note is from the previous program to this program, you will have x, which is a solution for this equation, coming out as two vectors, as what we have seen, two vectors, two column vectors, because first column will represent the displacement and the second column will represent the velocity, right? So once you have x to be estimated, you have to first estimate x, the displacement solution using the first differential equation, and then estimate the velocity using the second differential equation. So for that you will have two k's, k1 coming for the displacement and k1 coming for the velocity. Okay, so with that what you will have to do is you have to make a small modifications to get the value of new value of x and tabulate that carefully. Okay, so now if you see in the previous code, all the columns comma 1 here and all the columns comma 1 will give me the initial case x0. Now x0 is now a 2 row and 1 column vector. So that's the initial guess that we had. In the previous problem we had x0 to be only 1 cross 1 value, which is a scalar value. It was not a vector. So here what you have to do is take x0 as a column vector. Okay, this will give me the initial condition for displacement and this will give me the initial condition for velocity. Now after I do that, you will have the time step, which is 0.1 seconds, and time is varied, and this is where you will try to create. You will have two rows. First row entries are for displacement, the second row entries for velocity. So if you use this these two commands and run the same code, you will see that you would have solved RK4 method for system of differential equation. Now you have two differential equations and you have solved for both of this differential equation, and they're coupled differential equation in displacement and velocity. So you will solve the value of displacement in time and as well as for the velocity in time using RK4 method. So if I do this and plot that solution, RK4 method will represent a red square in the plot. So if I run this code again, okay, let me quit this debugging, take out these points here. Yes, all right. So if I run this code, you will see that your RK4 had a uniform time step from 0 to 0.1, 0.1 to 0.2, 0.2 to 0.3, so on and so forth. You took a time step of 0.1, so you had RK4 to estimate the slopes at uniform time interval. Whereas our ODE45, okay, I will run it again because I've used a hold on command. Just 1 second. Give me 1 second. Okay. Yes. Yes, here it is. So if I use RK4, it is computing the derivatives at the equal interval of time. Whereas if I use this ODE45, it is taking adaptive time stepping algorithm to estimate the times at different time steps. Okay, so all of them actually fall on the exact solution. So you will have a numerical solution from ODE45 and RK4, and you have exact solution from your integration, double integration, and you can also use desolve, or you can also use Laplace transform. Okay, so in this way you have accomplished how to solve differential equation, which is from Newton's law, from 4 methods. Okay, all right. So next, what we try to do, we'll take some more case studies. Case 3. Now, before I move on to case 3, did I paste the code for RK4? Yes. Did I paste the code for RK4? Okay, I'll try to do that. So here is a code that I have here. Okay, I'll try to paste that code. All right. Okay, sir, here it comes. Yes. That's the code for RK4. And I have to also give you the yes, the plot command is also there. All right. Now let me take case 3. Case 3, we will try to take up a problem for a second order differential equation that will represent the vibration of a mass, okay, when it is subjected to an initial condition alone with no external force applied. So it is a free vibration problem. Now you will see that the force applied, the initial conditions that is applied to the mass are your displacement and velocity. I will again set them to 0, okay, or maybe give a corresponding value of initial conditions by setting a displacement or velocity. Okay, I will have to define my spring constant K, okay, because the spring is going to give me a force which opposes the motion of the mass. That is by the Hooke's law, F equals kx, and the opposing force as given by the dash plot onto the mass is already known to us, that F equals c into the velocity of the mass. Okay, so that is given by c into x dot here, plus kx equals 0. So this is the differential equation of motion of the mass for the free vibration of the mass. So if you just set up initial condition, the mass is going to oscillate because there is a conversion of energy from kinetic energy to potential energy and so on and so forth. However, there is a dissipating element which is a dash plot here, so your energy has to dissipate for every cycle of oscillation. Now this is a second order differential equation. So what we try to do here is again solve this using ODE45 solver. Okay, I will not be discussing RK4 method in this example or case study. So what I'll try to do is I will try to help you out of how to actually get a first order differential equation for this second order differential equation. So if I take two variables again, x representing a displacement, I'll call it as x1, x2 representing the velocity, which is derivative of the displacement, then I can write two differential equation of first order in the following way. X1 dot is equal to X2. Then once I have this here, I can substitute X2 back here. So this will be M into X2 dot plus Cx2 dot plus Kx1 is equal to 0. So with that, I can get X2 dot is equal to minus Cx2 minus Kx1 divided by M. So these are your two first order differential equations that got reduced from your second order differential, and these two equations have to be now put in the function file to obtain how an oscillatory motion to a mass is obtained in time. Okay, so let us accomplish that. Okay, so if you see this, this two differential equation that got established, first order differential equation that got established is written here. My first derivative of the displacement is velocity, that is what I've written. The second equation is what I've explained before, which is minus C times X2 minus K times X1 divided by M. Now what I'll try to do is I'll take certain value of spring stiffness, mass value, and C. Okay, so if I take these values, I will have to vary C to see how the dissipation takes place for every oscillation of the mass. So this is the first two equations that I've coded up in the script. Then the main script is pretty simpler because you have to only define your initial conditions and you have to give the time interval. Then you will have to define this function, which is d spring mass dashpot of M here. So that will actually send two values as a vector. First value will be displacement, the second value will be your velocity. Okay, so you give your time interval and your initial conditions and solve this problem. So whatever t that you get from ODE 45 is the time, and whatever displacement that you get here is yeah, 2 cross an n cross 2 column vector, where the first column of x will represent the displacement values, the second column will represent the velocity values. Okay, so once you get this time and displacement, you can plot the time and displacement and see how it varies. So this is a plot of time versus displacement of a vibrating spring mass dashboard system. So if you run this code, you will see that for C, the dissipation or the dissipating element, if I make it as 2, suppose I make it as 2, a value of 2, okay, then you will see that the plot appears in such a way that the displacement varies with time, however, but it is not undergoing oscillation because the displacement is tending to 0 almost for time t equals 20 seconds. Now suppose I change the value of C, okay, I change the value of C to a specific value, okay. Now let me rerun the code. Okay, it did not even still change. So what I did was that I took the value of C to be in such a way that it was a critically damped condition. Okay, so that's a condition where the mass will not undergo an oscillation. Okay, suppose I give C to be 0, that means I will have absolutely no damping in the system. Then there is an exchange of kinetic energy with respect to the potential energy, so the mass will execute a simple harmonic motion. Here you see that. So there is an oscillation, sustained oscillation that keeps on going in time, because there is no dissipation for every cycle of oscillation, you see. So this was a critically damped case, and this was your undamped case, right? So suppose I make C to have a certain value. Suppose I make C to be 0.5. I've worked it out already. Suppose I make C to be 0.5, and I run this code again. You will see that the oscillations actually damped down. Okay, so you had a dissipation that took place to see that for every cycle of oscillation you had certain damping. Let's see. Okay, so in this way, by varying the system parameters such as your damping constant, which is C, okay, you can observe that the um, the vibration sets up in the system to have either an undamped motion or a damped motion or critically damped motion. Okay, so that is another example that we have here. So what I'll try to do is I'll copy this code and paste it up in the chat. There you go. Then we have the function, right? We also have the function here. Okay, so there you go. Now what we'll try to do is also go for case 4 very quickly. It's a forced vibration problem. Okay, so instead of setting the mass to undergo a motion with only initial conditions, now we will superimpose this problem. We'll set up initial conditions as well as just 1 second. Yes, we will try to apply the external force to the mass. Okay. Now let's think that we have a force which introduces a unit step displacement. Okay, to this system. Okay, so I can write the two differential equations of first order in this form, again by using the same method that I explained. Okay, so what we'll have is an additional term plus f here. That's the only change that you can see. The previous case that you had here, okay, you'll only have an addition of force term here. That's all. So the function scripts have to be just changed by including the force term here. Okay. Now what I'll try to do is this equation I'll try to modify. Okay. What I'll try to do is I'll use this damping ratio to first I'll divide this equation by f and then define two important quantities, which is my natural frequency. K by m will give me my natural frequency, which is omega n square, and zeta is given by c by 2m omega n here. And on the other side, if I divide f by k, okay, you will get c of t. Okay, you'll get c of t. You are dividing the whole equation by m first, and then doing a manipulation by multiplying, dividing by k on the other side, on the right hand side, so that you'll get f of t by k as an equivalent displacement c of t. So the resulting equation, okay, this equation turns out to be in this form. Okay, now you have to again write these two differential equations, right, for these two for this class of differential equation. And when c of t, which is a unit step displacement that's given to the mass, is known, then we will estimate what is the response x by solving this differential equation. So for unit step function that is applied to the mass m, we will see what is the displacement, variation of displacement in time. So the initial conditions are always set to 0 in this problem, and c of t is set to be 1. For that, you have a standard solution, analytical solution. Okay, if you use dsolve, you can get this solution. So that solution is defined in terms of damped frequency known as omega d. Omega d is omega n into root of 1 minus zeta square. Okay, if zeta is equal to 0, it becomes an harmonic motion. Okay, so we will try to take up a code and see how we can understand the response of the system. Here it is. So what I've done again is write two differential equation from the second order differential equation. So differential equation that I have here, these are the two differential equation, and unity stands for that I have C of t equals 1, which is unit step displacement. I will take a certain value of the damping ratio, okay, and define the natural frequencies, which is 1 for this system. Now and define what is omega d and plot the exact solution here, and then use ODE 45. Okay, we have just done the same thing, but only to include the term force here. That's all, nothing else. So if I run this program, so you will see, okay, I have to just run this. Okay, yeah. Okay, you will see that these dotted points are from ODE 45 solvers. Okay, so it takes adaptive time step for giving the solution. But what I've done here is also take and plot an exact solution for a particular value of zeta. Okay, so if I take this is the exact solution, and this is the C of t, that is a unit step that's given to the system. So if a unit step is given to the system with a certain value of zeta, now what is the value of zeta that I've set here is 0.707. Suppose I give it as 0.707 here, 707, and rerun the code, you will see that this is the response that you got. The ODE 45 solver did solve the equation, and you had the data points of ODE 45 sitting right on the exact solution that we have given there, that you saw in this previous slide. So this is the exact solution that I have here, and yeah, this is a plot that I have here. Okay, so for zeta equals 0.707, if you can think that that's the optimal solution for the displacement. If you increase zeta a little bit, then your system response will become slower and slower. Okay, so this is also an example of how you will solve an ODE, second order differential equation, for a spring mass dashpot system subjected to a unit step displacement. So I'll try to conclude because the time is running out. So what we'll have is in this session we had discussed how to solve analytical and exact methods using dsolve command, using Laplace solution, also by using integration schemes. Then we discussed also the numerical methods, which is ODE 45 solver and RK4 method. We understood that there was an error from RK4 method, and that error was of the order of time step to the power of 5. Okay, it is a local error. Okay, then we again adapted ourselves to choose a method so that the error got decreased. So we used ODE 45 and compared that with the exact solution. We saw that there was some error. Okay, then we use the choice of method that depends on the type of differential equation that we were trying to solve. Okay, so each differential equation will have its own governing physics, like free vibration case and as what was discussed in the forced vibration case. Okay, and meanwhile, before I conclude, I will try to send you this code. for your forced response. Here it is in the chat. Okay, so that should conclude my talk. So I have concluded. Thank you. So if you have any doubts, you can write a mail.